this number theory, I think I just want to at least outline what we're doing. So we have for continued fractions,
Alright.
yeah,
Oh,
continued.
infinite continued fraction.
Yeah, so we said the continued fractions are finite if and only if it's rational, yeah?
Alright.
And then so we have infinite is irrational, yeah? Okay. And then we have that, and then so the chapter that we're up to is talking about periodic continued fractions. So if you remember when we did it for root 2, root 2 equals like 1, and then like 2 repeater or something like this, yeah? This is like a periodic continued fraction, and I think what the goal of this chapter is going to be is to prove that essentially these square root things are the periodic continued fractions.
Like all algebraic or just square root?
So like, let's see. It's like the root of a quadratic. It's the root of a quadratic with integer coefficients or something like this.
Just like a plus b root c or rational a.
Yeah, maybe that's another way to express it. Yeah. So like, yeah. So it kind of. Yes. Maybe we can do an example. So apparently it's easy to prove if it is periodic that you get that, but it's not so easy to prove that if you have the root, it's always going to be a periodic.
I think the other way is just like you sub in the part that isn't.
Oh yes. Okay, so we have something repeating, yeah. So it's like A1, or like A2, A3. Let's say the A2, A3 are repeating, yeah. How do we prove this is like a root something?
You let it be like x.
So x equals A1 plus 1 on A2 plus 1 on A3 plus, and then here it's like
A2.
So like, is it 1 on x minus A1? Is that what that is?
I don't think that's like. Yeah.
Yeah.
Yeah, you can do it. And then it's put it after multiplying.
Oh, maybe it's just x minus A1. I wrote 1 on x minus A1.
Yeah. It's just x minus. Yeah. When you flip everything into the degree can't be more than a quadratic.
Okay, so how do we do this? Let's see. Yeah, so no matter how long the period is, you just keep going longer, right?
Yeah.
What you would get, and you get the last, this bit here, A2, A3 plus A2x minus A1, A2. So that's in the numerator, which becomes the denominator, yeah? And then in the numerator it becomes A3 plus x minus A1, and we're plussing this to A1, yeah?
There's also plus 1.
Plus 1. Oh dear. +1. Yeah.
I think you improve like all the way up to like the right hand side. You get it to be like a linear in x over a linear in x,
Ah, yes.
and then after you times it over, it's most of the variable.
The left-hand side is like quadratic, and the right-hand side is linear.
Yeah.
Yeah. Okay, that sounds pretty good. What does that sound? Okay. Let's see what they have to say about this. Yeah, so Anthony, you're convinced by that?
Yeah.
You mean convinced? Hmm. Okay, maybe not convinced. Okay, so what don't you get? So if you have a periodic part, right, that kind of just means you can replace the tail by some formula in x which doesn't have any x squareds in it. And if you do the reciprocating and plussing and stuff, you still won't get any x squareds in it. You'll get like x's over x's. And then when you clear the denominator at the very end, you might get some x squareds from the left hand side because there's an x times some x's. And then on the right hand side, there's yes, it is also probably towards the end of your concentration span. Yeah, the right hand side just has x's in it. Okay, let's have a look. There's some interesting historical comments about when this was proved, actually. Yeah, so we dealt mainly with the expansion of quadratic irrationals or quadratic surds with rationals of the form p plus or minus root d on q. Okay. So it was first proved by Lagrange in 1770. So the more difficult theorem that any quadratic irrational has a continued fraction expansion which is periodic after a certain stage. So eventually periodic.
Lagrange is a recurring.
Yeah. First, it will be shown that a periodic continued fraction represents a quadratic irrational of a special kind, called a reduced quadratic irrational. So what does purely periodic mean?
So A1 is also part of the recurring part.
So it's not eventually periodic, it's already, it starts off periodic. Oh.
2 plus 1 over 2 plus 1.
Okay, so that's like all of section 4.1. Section 4.2 and is followed by proof of a general case. So that's the first two sections is just doing that.
Yeah.
So it's really just a very simple exercise. Okay, and then section 4.3, quadratic irrationals. Section 4.4, deeper study of reduced quadratic irrationals.
These sections contain the tools necessary for proving in section 4.5.
That any reduced quadratic irrational has a periodic continued fraction expansion. This is followed by the proof which states that the continued fraction of any quadratic irrational is periodic from some point on. Okay.
Very spicy.
Yes. The chapter will end with a brief discussion of the Pell's equation, which was not done by
Oh.
Pell, but apparently Pell got attributed to it because Pell is such a genius. Apparently Pell,
At the age of
so he's rated 1 on the scholar criteria.
for Harvard.
Yeah, apparently, I don't know.
Wow.
But I don't know if Harvard was even
Is
around at
one
that
good?
date. The one's the highest.
Oh,
So a summa cum laude material. Okay, so he went to uni at 13, mastered 8 languages before he was 20.
irrelevant to math.
Yeah, you can't. There's nothing else to do at that time, right? You just read languages, and in England, you actually have a chance to use them over there because there's like people neighboring that.
In Europe.
He was a professor of mathematics at Amsterdam, and he was
So he was
Cromwell's
just a great
representative.
teacher.
Cromwell's representative in Switzerland. What does that mean? Or maybe
He
that
was
was at the
elected
time of
a
Thomas
fellow-
More.
What's the last sentence?
He was elected a fellow of the Royal Society in 16. Yeah,
He was a friend of the Royal Society.
a fellow.
Othello.
No. Yeah, no, like people think the Royal Society is such a big deal. It's like finally they accepted Ramanujan into the Royal Society, as if like now we can finally respect him as a person or a mathematician, whereas before he was just kind of good.
Feels okay.
Yeah, but like you wouldn't know it because the authority of God had not deemed it so.
He was
Yeah.
a
Yeah, these pretentious pricks. Okay, elitism. Empty elitism. Okay, so purely periodic continued fraction. What? Oh, section 4.1 is just the intro. Wow, this book is
Well, what's
so.
that? What's that? X squared minus 4 million.
Oh, that was about the cattle.
So this book is actually really friendly. Like you could probably read this book, like when you're in year 5. Obviously, you'll be reading it very slowly, but like it'd be a very interesting read from like year 5 to year 10. I think if you like the first year 5 to year 6, you read like 3 pages. Year 6 to year 7, you read like 10 or 20 pages. Yeah. Year 7 to year 8, you read like you just keep doubling. Yeah. Okay, so certain continued fractions are periodic, like root 11 is only periodic after the 3, yeah? But root 11 plus 3, oh, see? That's how you make it pure. Oh, so it seems like you can convert it almost to purely periodic somehow. Periodic. So that's 3 because so if it's not periodic at the first one, you can just add something to make it periodic. Or minus something, yeah? So like if it was like 736 repeater, you could just minus 1, and it'll be 63 repeater.
Was that always there?
Yeah, no, it's
What?
only for the first time.
We only observed it for the first time just then.
Yes.
Okay. Oh yeah, it does always like first time. Yeah, you can make the first digit whatever you want. So you just add it to the sequence.
Yeah. So maybe that's the difference between a purely periodic one and an eventually periodic one. And maybe that is the difference between a reduced irrational.
I really hate this format for writing the fraction.
Oh, that disgusting. Add fraction sum.
I think that it is very dodgy.
From other quadratic irrationals.
A equals 4.5. Oh no, what's it called? 9 over 2 plus 1 over A.
A numerical example. Consider some purely continued fractions, purely periodic. So 312 repeater.
Of alpha.
Yes.
Oh, I
So-
know the answer. If it's like A is 9/2.
Oh.
That's the one.
What were the numbers again?
6.
3, 2, 1. Was it
Close
3?
one.
Just here. 3, 1, 2.
Yeah,
Okay,
3,
3,
1,
1,
2.
2 is like 3 plus 1 plus 1 on 2, right?
Yeah.
And then it
Plus
just
alpha.
repeats again. Plus 1 on alpha.
Yeah.
Wow.
Yes. Two alpha plus 1 and alpha.
2 alpha plus 1 alpha. Yeah, their notation made it confusing a little bit there. Okay, and then you can solve this for a quadratic somehow. Okay, but we were interested in some sort of property that this quadratic has.
Results starting with we should that if
Ah, yes, you remember this one?
OMG. AN plus 1 equals
Yes, that is indeed true. Yeah, so I think you have to be careful to distinguish the alphas from the A's, yeah?
Yes.
Yeah.
So the A's are the things for which they're the integers, yeah?
Yeah.
Whereas the alpha is like the tail.
The infinite table.
Yeah, so but if you pretend the tail is an alpha, you can kind of treat it like the A's when you have a finite number of them. Like you have a finite number of A's, and the last A is just equal to some alpha. Okay, so we indeed had this from earlier. So as far as we're concerned right now, we're assuming this, okay? If you want to know why that's true, we'll have to look at a previous venture. Okay. Okay, so they explain it a little bit more, okay? But in the case of a purely pure continued fraction, we see that
Whoa, crazy.
what just happened? Yeah, we already have that, yeah? So the alpha n plus 1 is alpha because it's the same as before, right?
Yeah.
Ah, okay, that's a natural next step, just to replace the alpha n plus 1 by alpha, yeah?
We now apply the special.
Oh. Oh, wait. Okay. Well, that already that's probably a faster way to show it's a quadratic, yeah? Because that'll give you instant quadratic in alpha.
Yeah.
Okay, so what's a special case 4.2? So that's the 312 thing, yeah?
Form the table.
Form the table. Oh, so n is the first time it's the last time it doesn't repeat.
How do you solve? So I got the for the 312 I got the a squared is like a linear function.
What in what? What? What is that?
Oh, that's the alpha.
Is that also alpha?
Yeah, that's also
Oh.
simpler to write as a. Yes.
Okay, maybe it's good. Okay, maybe let's just do this example ourselves. How about that? So just remember this formula, yeah? So it's Pn. Yeah, it's just alphas and Pn minus 1.
Alright.
Okay, so what do we have? We have a continued fraction that's 3, 1, 2 repeater, yeah? And we have that alpha equals alpha times P3, yeah? Plus P2 over alpha Q3 plus Q2, yeah?
Yes.
Okay, how do we find out P3 and P2? Well, let's just expand this. So you have that. So P2 over Q2. So there's actually like a recurrence that helps, but you know, we could do it. So like P1, we can do it all the way, just for the sake of it, yeah. P1 on Q1 is 3 on 1, yeah. P2 on Q2 is, so it's 3 plus 1 on 1. That's 4 on 1. And then you plus 1 on 2, yeah. So that's 3 and 2/3. That's 11 on 9. 11 on 3. So then this is equal to 11 on 3 alpha plus, sorry, 11 alpha plus 4 on alpha plus 3 alpha plus 1. Alright?
Yes.
Okay, actually, I think this is probably what the book says as well. See? Yeah.
Whoa.
We skipped the table confusion.
Yeah.
Okay, and then 3 alpha squared plus alpha equals, so just equating these, yeah? 11 alpha plus 4.
Alright, yeah. I got 3.6.
Why? Why?
Let me check. So it's like 10 plus minus root 140.
Okay, I guess we'll just do the
6.
plus. 10 plus
Yeah, but it's only plus because otherwise, yeah.
100 plus 648.
Plus 48.
That's more than 12.
Yeah.
By a little bit.
Yeah. Over 6.
Over 6. Yeah.
So that's equal to 5 plus 25 plus 12 over 3. 37.
37 over 3. Yeah. So why is this reduced? Something about this is reduced. And it's not the plus.
I guess that's something to do with co-privacy.
Co-prime.
Oh, okay, so this is actually part of the theorem as well. So if you reverse it from 213, so from 312 to 213, you also get
Very weird.
You also get it's claiming you get it's 4, the 4 and the 3 are swapped, yeah?
Why?
Why indeed? I guess this is an example to illustrate the claim of the theorem. So let's just do it, yeah? So
213.
So if you do 213 repeater, yeah?
Wrong.
You have alpha equals, so remember we just need to calculate the convergence, yeah? That's alpha P3 plus P2 on alpha PQ3 plus Q2, yeah. we can use another way to try to figure out the convergence. So, for example, we know P1 on Q1 is just always the first number on 1, yeah? Q2, P2 on Q2 is just 3 on 1, and then we can try to use the recurrence to get Q3, yeah? P3 equals 3 times P2 plus P1, yeah?
Wow.
Yes.
11 on 4.
So this is 11 alpha, 4 alpha plus 1 plus 3, yeah? That's what they claimed. That's beta. They wrote beta this time.
Beta.
And it satisfies 4 beta squared minus 10 beta minus 3. So it's the same equation, is it? Is it the same equation? No.
Oh, that's what confused me. The beta. It was the same thing, but instead of divided by 3, it was divided by 4.
Oh, okay. So it's the same equation. Oh, okay. So it's the same equation, but with the first and last numbers swapped, yeah?
Yes.
Before it was 3 and 4, now it's 4 and 3. So if you replace it by -1 on beta, you should actually manage to swap it into the same equation. You know?
What?
Yeah.
What the hell? Why is it negative?
Oh, because you need the first and last things have opposite signs. So you need the 4 to turn into a -4, and the 3 to turn into a +3. What? But then the 10 turns into a +10. Do we have a +10?
Plus 10.
Three squared. +3.
Has solution.
So I mean, I think you just have to check.
-1.
Yeah. So if you check, does it work? So if it's minus, right?
Yeah.
Then you get 3 on beta squared, yeah? Plus 10 on beta. Minus 4 equals 0, yeah? And then you get, if you times everything by -1, you get 4 beta squared minus 10 beta minus 3, right?
Yeah,
But if you didn't do the minus thing, then this thing would be the wrong sign. Okay, good.
Is reversing the period just reversing the order of things?
yes.
Yeah, that's what they mean, yeah. Reversing.
So the alpha equals -1 on beta.
Yeah, so the roots of the quadratic are related.
Oh, no. Four.
Huh?
Wait a second. What's the... Oh.
So these roots cannot be equal since one is positive and one is negative. Moreover, beta is greater than 1. Why is that?
This goes fine.
Oh,
This starts with a 2.
3, 1, 2. Oh no, but it's saying beta is always greater than 1. No matter what the number is.
Essentially just define that you can Bulgogi start with a positive.
Yeah.
They're just Bulgogi A1.
A1 is positive. Yeah.
That gives you logic.
Yeah, like you can't have zeros at the end, right?
No.
So
They can't have zeros at all.
you can't have zeros at all. Yes. Ah, so you can't have a 0 at the start then.
Yeah, you can't. You can't have the. No, I think you can have the 0 at the start.
I think you can't have 0 at the start because if it's periodic, the 0 will have to repeat. You can't have zeros in the middle.
Yeah.
So therefore you can't have zeros at the start.
Yeah, exactly.
Yeah.
So it's a consequence.
Yeah.
That's if it's the what's it called, the pure periodic thing.
Purely periodic, yeah.
Yeah.
So that means the beta has to be greater than 1. Negative beta must 1 on beta must be less than 1. So negative 1 on beta must be between negative 1 and 0.
Yeah.
Okay. It is easy to check these results numerically. Oh yeah, well, okay. We don't have to worry about this.
Mm.
Okay, so I think this is a good prelude to the general case. And we might even end it there for now, but like, oh, I don't know how much momentum we have, but the general case. We shall prove that, yeah, so if you have alpha is purely periodic, yeah, it's greater than 1. It has to be greater than 1, right?
Yeah. The purely periodic sections.
Is greater than 1. Yeah, they're saying is greater than 1, right?
Yes.
Oh, but it's saying positive integers.
Yeah, so it has to be greater.
But in the theorem, it assumes it's greater than 1. Whatever. Okay, so the purely periodic continued fraction alpha
Oh my god.
is greater than 1 and is the positive root of a quadratic equation with integer coefficients. Moreover, if you reverse it, you get beta, then negative 1 on beta is the other root. You know? So that's what we saw in the example. But it's claiming it holds in general.
Yes. Really important. A prime arrived in negative.
Yeah. Why is that equally important?
Mm.
Suspicious.
Then
Okay, we require 2 results stated in problem 7. Oh, look at that. We actually did that problem.
whoa.
Who would have thought that would have... Because that was the reversal. That came to mind, right?
Yeah.
Yeah. It just kind of came to mind, but we didn't use it, so we kind of just left it there in the back of one's mind.
Swap the root.
Okay, why is there primes? Why is there prime there?
They represent the nth and n minus 1st convergence. Yeah, it's just like the other continued fraction of
Beta.
the reverse. Yeah.
Oh.
So,
Oh. Yeah. So if you just do the Pn on Pn minus 1, you get the reverse.
yeah.
Get the reverse. I'm slightly confused. Slightly confused because it's infinite, right?
So that's why they're taking like the nth convergence.
Yeah.
They don't need.
Oh. Okay.
Since convergence in the last term.
Where's the proof conclude?
At the problem set, page 96.
So the proof concludes in 2 pages. 2-page proof.
Average Tottenham Towns question.
2 pages is like.
Yeah, average Tottenham Towns question.
That is like way below average. Average is like.
What Tottenham Towns?
Since convergents are in their lowest terms, it follows that. Okay, let's see if that's true. So if we look at these things, Pn on Pn minus 1 equals Pn prime on Qn prime. Do we know that Pn on Pn minus 1 is in the lowest terms?
Yes.
Yes. convergence.
Co-prime by
Yeah, they have to
induction.
be yeah, they have to be co-prime.
They have to be co-prime.
Yeah.
They all have a common factor then. Wait, what's co-prime? So is P
Co-prime is they have no common
Oh, yeah.
factors apart from one.
yeah, like is Pn co-prime to Pn minus one?
Yeah,
Okay, why is that?
because
Explains to us. I think things to do by induction. Because use the recurrence and then
Oh, okay.
Yeah.
So if ever it's not co-prime, it'll be a common factor to everything below.
yeah, so yeah, you use induction, and then so let's say there's a factor just say that one of the factors, the first factor has to be co-prime, right?
so why is that bad?
Oh, first one, that's clear. It's 1 plus 1 over something. So it's like integer plus 1 over integer. Gosh. Oh yeah, so it's a1 plus it's a1 a2 plus 1, yeah?
Yeah,
Which is co-prime.
Yeah.
and then you flip it, and then you add stuff, so it's always co-prime because when you multiply the two things, when you add a certain amount of
Yeah.
yeah.
Okay, so then the Qn on Qn minus 2 is Qn minus 1 is co-prime because the first Q is just 1, right? So excellent. Okay, so then it is true. So basically what we're saying is if you have two fractions equal to each other, we can equate the numerators and the denominators if they're both reduced, yeah. Okay, so Pm prime is equal to Pn. Oh, Yasser has arrived. Okay. It follows that Pn prime equals Pn minus 1 prime equals Qn. Yeah. Yeah. Yeah, so the left column is the first, and the second column is the second fraction. Yeah, so Pn equals Pn prime, Pn minus 1 equals Qn prime, Qn equals Pn minus 1 prime, and Qn equals Qn minus 1 prime. Okay, since alpha is purely periodic, we can do this thing like before, yeah? This thing. Ah, so now we're trying to replace them by some kind of sum of roots, product of roots going on maybe?
It's
because we only need the nth convergence, huh?
reversal.
Yeah, so basically just clear denominators and you get this. What is up? Did you see our construction for JA6? You have to watch the video, I guess.
No.
Like everyone else.
What number do you construct it for?
What number?
Not S6.
JA6.
Oh wait, the wizard.
The medals.
I was thinking about the wizards.
Oh, the medals, but
Yeah.
Hold on. So is it?
oh wait, the answer is yes or no? Yes, you can.
Awesome.
Possible. And we proved it by proving it is impossible. That was the method of rough working.
We thought it was impossible, so we were trying to prove that it was impossible.
Oh, right.
And then we proved that it was basically a unique possibility. Well, not unique, but like Very, very,
Very close to being impossible.
very close one.
Oh yeah. You know what hard question is almost never impossible to do. There's no
Well, it would have been a very difficult write-up, which we attempted to do. And yeah, it was also that we also proved that you can't use the argument that you can double the silvers.
Yeah.
You can't do 28 and 27.
So
Like you,
those people are getting 0.
yeah, like you can't just say like the set like a silver medal counts as 2 medals. So therefore there's 28 possibilities and only 27 outcomes. You're not allowed to say that. Yeah, everyone.
Basically, a lot of people did it.
Okay, so
Now that's
as the n and n minus first convergence, yeah, equation is equivalent to the quadratic equation. That, yeah. So we just clear the denominator, and that's what you get. Okay, so reversing the period, you get the beta, and the beta you get this, yeah. I'm sure this will work.
yeah. This is all of us.
Oh, okay. So now we can replace the Pm prime by the P. What was the things they were? Pn prime by Pn, yeah. Pn minus 1 prime by Qn, yes. Qn prime by Pn minus 1, okay, and then we arrive at Qn minus 1. So we do get that, yeah?
Yep.
That's perfect. So I guess we just form the quadratic and then do the -1 on beta thing, yeah?
Yes.
Okay, let me just check if this is the quadratic you form here. So get Qn alpha squared, yes. Qn minus 1, yes. Pn minus Pn, yes. Minus Pn minus 1, yes. Okay, so let me check if this quadratic, the next quadratic is going to be the right one. So we're proving if a continued fraction is purely periodic, as in it's periodic right from the start,
Yeah.
then it has to be the root of a quadratic equation with integer coefficients, and its other root is. Wait, you haven't finished stuff.
It's 1 plus 1 over 1 plus 1 over then kind of
Yeah, so that's,
on both sides equation of
yeah, you got to hear the end of it. There's more conditions. So even if it wasn't purely periodic, that would be true, yeah. But what's also true, and what makes it purely periodic, and I guess this is also probably what the definition of reduced irrational or something, quadratic irrational, is that the other root of that equation can be obtained from the first continued fraction by reversing it and negative reciprocating the number. That's what we're proving right now. Yes, welcome to Math World. Okay, so this equation is Pn minus 1 beta squared, yes. Plus Qn minus 1 beta, yes. Minus Pn beta, yes. Minus Qn, yeah? So those two equations differ. So, okay, so if you look at these two equations, let me just write these in blue. You look at these two, so we look at this equation, yeah, and this equation, yeah. So that's the quadratic you get from reversing the periodic fraction, and that's the one you get from the original continued fraction, okay? So the middle is the same, and the outsides are the swaps of each other with a minus sign, right?
divide by alpha squared.
Yeah, so if you replace,
Divide by alpha squared, then it's going to be the new beta.
yeah, basically if you replace alpha by -1 on alpha, or replace alpha by -1 on beta,
Yes.
then you get the bottom equation for beta. Okay.
Yes.
Yes.
Okay.
Okay, let's clear
So
some.
the alpha equals alpha. So Pn is the Pn minus 1 is this formula for the. That's the formula from earlier.
No. Okay.
Oh wait, that's so genius. Wait.
Comparing equations that we conclude that it has two roots, yeah? Okay, so we already discussed this. So and then beta is always bigger than 1 because the first if it's periodic it can't start with a 0 because the 0 can't come up later.
Something. Why is the Pn? Why is the Pn's in the betas the same as the alpha?
It's because of that lemma it was an exercise that showed that if you reversed the continued fraction thing,
Yeah.
you get Pn on Pn minus 1. You remember that?
Okay.
So basically Pn on Pn minus 1 is equal to like Pn prime on Qn prime. So that's
What
the
is primes.
primes is like the actual convergence of the reversed continued fraction, whereas the non-primes are the convergence of the original continued fraction. That makes
So these
sense.
turn out.
So that's this thing
Be-
here.
They turn out to be equal.
They're not.
No, they're not exactly equal, but they're
The ratio.
very closely related, like this. Yeah.
Some of them.
P prime of n minus 1 is Qn. This previous now.
Yeah. So basically, like remember when you have Pn on Pn minus 1, you get the continued fraction with all the parts are reversed. Yeah.
Thank you.
Uh,
Can't remember that.
So yeah, it was the very first exercise that had a star. Remember? That you kind of
It was a long while.
Last week thing.
yeah.
Was it the exercise I did?
Maybe you went around it. I don't know. Okay, so back to this. Okay, so the converse of theorem 4.1 is also true. Or what is the converse? It means that if alpha is a quadratic irrational and hence satisfies the quadratic equation with integral coefficient, the second root lies between -1 and 0, then the continued fraction expansion of alpha is purely periodic. This remarkable fact was first proved by Galois. What?
Wow.
What? 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 It needs to be investigated now. What the hell?
Alpha greater than 1 quadratic rational number. Hence.
Recurring character. Hold on, what was theorem 4.1? So theorem 4.1 is this. If you have a purely periodic fraction greater than 1, it's the root of a quadratic equation with integral coefficients. Its negative reciprocal of the reversed fraction is the other root and lies between -1 and 0. So what is even the converse of this statement? So he's saying that if alpha is greater than 1 is the root of a quadratic irrational is the root of a quadratic equation with integer coefficients. And if the other root lies between -1 and 0, then the continued fraction of alpha is purely periodic. Oh. I guess that also means that the other root is the negative of the
Converse of the.
Oh, okay. So it's the converse of the statement that if alpha is purely periodic, it has a purely periodic continued fraction, then it's the root of a quadratic with integer coefficients, and the other root is between -1 and 0. Yeah.
Yes.
So if that's the that means if both roots are, so if one is between -1 and 0 and the other one's greater than 1, and they're both roots of a quadratic equation with integer coefficients, then the continued fraction of alpha is purely periodic. Oh, and I guess therefore the beta is also the other root is also the negative reciprocal of the reversed continued fraction.
So it's just how did so these are just inequalities. So how did inequalities suddenly turn into some exact thing?
Yeah. Yeah, so you're wondering if even if it's true, yeah, let alone how to prove it. Though the result was implicit in the earlier work of Lagrange. Oh my gosh.
Implicit.
It's like when people really care about you, they really look for the things that help you. It's like even though Lagrange didn't, this is like Lucas's write-ups. So even though Lagrange didn't state it explicitly,
It was
we have to imagine that he actually wrote it and give him credit for it. Yeah. Lagrange Callow. Galois in 1828. Oh, because Lagrange was 1770, yeah? That's like a 50-year gap, 60-year gap. What is to be emphasized is that these few conditions in alpha and alpha prime completely characterize the numbers which have purely periodic continued fractions. So these, I guess, are what's called reduced quadratic irrationals.
It's literally just
What happens if alpha?
I swear if you just made an exam testing people to remember the definitions, they wouldn't be able to do it.
Yeah.
Like the non-maths people.
So you have the alpha prime. So does it mean the continued fraction expression of alpha prime is the reverse thing as well in calculus?
Wait, is alpha prime the other root?
Yeah,
Okay, so if it's alpha prime's the other root, it's negative. So you have to make it positive by taking the negative reciprocal, you know. And the negative reciprocal of the second root is what has the continued fraction that's the reverse of the original continued fraction. It just sounds retarded.
Wait, product of roots.
Yeah. That's like, yeah, it's just saying the most simplest things precisely is like can be a bit of a headache because like you have to define the terms and then you have to string them together. Okay, hopefully Yiming is still following.
Isn't it 3 already?
Yeah.
Oh yeah,
Early mark, probably.
yeah, the early mark. I'm sorry. Maybe it'll be 3:30. We're almost done. We're at the bottom of the second page. Yeah. Okay. The summary sentence should make up for all the BS in between. So. Simple recurring continued fractions may be grouped as follows. Fractions have an acyclic non-repeating part. So that's purely periodic, yeah?
Yes.
Those with an acyclic part consisting of a single quotient, such as that. Oh. Or has those acyclic containing at least two quotients, such as that.
Alright.
Okay, so we proved the type 1 is a quadratic irrational which satisfies that condition, yeah? Cases 2 and 3 can also be proved that alpha is a quadratic irrational. So this is actually interesting because this is a part of the book that wasn't part of our previous discussions on continued fractions. We claimed certain things and never proved them. So here it's like, this is a golden opportunity to fill in those gaps or learn continued fractions again, yeah? It's almost like every time we want to learn something, we have to find a new book. Okay. The second root alpha prime of this quadratic is either less than -1 or greater than 0. Third case, the second root is necessarily greater than 0. We will not prove these last two results. Oh.
No.
Oh. Okay, so let's summarize what this.
Not proved.
Let's summarize what has been claimed in this chapter and what has been proved. Okay,
Proved.
is you
Not
mean
much.
here because this is probably like this one paragraph of words might make up for some of the others that weren't.
What phrases do you mean?
You mean the 8?
So,
Yeah.
Hmm.
Okay, so what this chapter claims. So I don't know. In 3, why does it have 3 A's? It's really just more 2 or more A's. Is that right?
Yeah.
Okay. Okay, so what this chapter is trying to what this section has claimed is that fractions like this, yeah, where it starts repeating from the get-go, are called purely periodic continued fractions.
Hmm.
Okay? And the numbers which they represent are exactly what's called the reduced quadratic irrationals. And they're the numbers which satisfy a quadratic equation with integer coefficients whose other root is also between -1 and 0. Okay. So actually, the thing which is proved, okay, the thing which has been proved is that if you have a purely periodic continued fraction like that, then it satisfies a quadratic equation with integer coefficients. Okay. And the reversed fraction satisfies the reversed fraction, and after you take the continued fraction expansion and you reverse the a's. So you put an first and then you put a1 last. That's like the beta, okay? And then you do -1 on beta, and -1 on beta is the other root of that quadratic.
Yeah.
Okay? And because beta is positive, -1 on beta is negative, and because beta is greater than 1, -1 on beta is between -1 and 0. Okay? So we proved that if you have a purely periodic continued fraction, then the quadratic equation has integer coefficients, and both the roots are within sort of the first one is just greater than 1, and the other one is between 0 and -1.
-1.
Yeah. Okay.
So how do we know that beta is not? How do we know that -1 of beta is not equal to alpha?
it's negative.
Because it's negative.
Negative. Yeah.
Alpha is positive.
Alpha and beta are positive.
Yeah. Alpha is greater than 1.
It's greater than 1. So say it's alpha greater than 1 in that final paragraph.
Oh no, it just has to be greater than 1 because of because little a1 is greater than 1 or 1 or greater. It can't be 0 because if it's 0, it won't repeat properly.
Okay.
Because you have to take a reciprocal of something. Okay, so yeah, does that make sense?
Mhm.
So what was proved was that if you have a continued fraction that's purely periodic, then and it's bigger than 1, right? The number is bigger than 1. Then the quadratic equation has a second root that's between 0 and -1. And the second root is obtained from reversing
Yeah.
the a's in the alpha to get the beta and taking the negative reciprocal of beta. Okay? So then what Galois proved was that all you needed to know was that an integer quadratic equation has a root that's greater than 1 and a root that's less than 0 and greater than -1. Yeah? Then all of those conditions would have to hold. So that's kind of crazy. So basically, what a reduced quadratic irrational is, it's a quadratic irrational whose quadratic equation has integer coefficients, and so it's a solution of a quadratic equation with integer coefficients, and the other root is between 0 and -1. Yeah. So it's greater than 1, the other root is between 0 and -1, and so the claim is that purely periodic continued fractions exactly represent reduced quadratic irrationals. Yeah. So the part for which that has not been proved. Yeah, so we didn't prove the part that showed that reduced quadratic irrationals were purely periodic continued fractions. That was the Galois part. The part that was proved here was that the purely periodic quadratic irrationals are these. Yeah. Okay, and then there's the cases of when there's It feels like case number 2, you just add something to make alpha 1 equal to beta 2 or beta n. Yeah. A1 add something or minus something to get to equal bn. But then that might affect the quadratic in a funny way. Alright, great. So that's a perfect point to stop. Alright, Yiming, thanks for staying. Hopefully that made sense. Wait, is Yiming still here?
Check. Oh, 2 people left.
Alright, see you. He's gone, I think. Wow.